In today's video, we're going to explore how electrolysis can be used to extract reactive metals from their metal oxides. This process begins by melting the metal oxides into molten ionic compounds, allowing their ions to move freely. As you might already know from previous lessons, many metals in nature exist in the form of oxides, such as aluminium oxide or copper oxide. In order to separate and obtain the pure metal, we need to remove the oxygen from the compound, a process known as reduction. Essentially, reduction means removing oxygen from a compound to get the pure metallic element. Now, the simplest and cheapest method for doing this is reduction with carbon. In this method, carbon atoms react with the metal oxide and displace the metal, producing pure metal and carbon dioxide gas. This works well for metals that are less reactive than carbon, such as zinc, iron, and copper. However, for more reactive metals, this method doesn't work because carbon simply isn't reactive enough to remove oxygen from their oxides. For these highly reactive metals, such as aluminium, we must use electrolysis instead. The downside is that electrolysis is a much more expensive process because it consumes a huge amount of electrical energy. As we learned before, electrolysis is a method of splitting ionic compounds into their pure elements by passing an electric current through an electrolyte. If our electrolyte is aluminium oxide, electrolysis can separate it into pure aluminium metal and oxygen gas. But there's one problem: for electrolysis to work, the ions must be free to move. Solid aluminium oxide doesn't allow that because its ions are locked in a rigid lattice structure. To make the ions mobile, aluminium oxide must first be converted into a molten state. However, aluminium oxide doesn't exist naturally in a pure form. It's found inside a mineral ore called bauxite. So, the first step before electrolysis can even begin is to extract and purify aluminium oxide from the bauxite ore. You don't need to memorize the detailed purification steps, but the key idea is that the end product must be pure aluminium oxide. Next, we must melt this aluminium oxide to make it molten. Only then can it act as a true electrolyte. But this presents another challenge. Aluminium oxide has an extremely high melting point, over 2000 degrees Celsius. To reduce that temperature, we mix the aluminium oxide with a mineral called cryolite, which lowers its melting point and makes the process more energy efficient. Even so, the temperatures required are still very high, meaning the process demands a significant amount of energy overall. So, to summarize, before we even begin electrolysis, we must first purify the aluminium oxide, then mix it with cryolite, and finally heat it until it becomes molten. Once we have our molten mixture, we can set up the electrolysis equipment. We'll need a beaker or suitable container to hold the molten aluminium oxide, which, remember, is our electrolyte. Then we place 2 electrodes, both made of carbon, into the molten mixture. Carbon is used because it conducts electricity and can withstand extremely high temperatures. On the right-hand side, we have the positive electrode, known as the anode, and on the left-hand side, the negative electrode, known as the cathode. These are connected by wires and attached to a power source, such as a battery. Once the power is switched on, electrons begin to flow through the circuit, and the process of electrolysis begins. Inside the molten aluminium oxide, we have 2 types of ions: oxygen ions, O2, and aluminium ions, Al3. Because they are negatively charged, the oxygen ions move towards the positive anode. When they reach it, they transfer their extra electrons to the anode, this is called discharge, and become neutral oxygen atoms. These atoms then pair up to form oxygen molecules, O2, which rise as oxygen gas and escape into the air. Meanwhile, at the negative cathode, the aluminium ions move towards the electrode and gain 3 electrons each, becoming neutral aluminium atoms. These atoms collect at the bottom of the container as molten aluminium metal. Over time, the liquid aluminium forms a shiny metallic layer at the base of the beaker. Let's now write the half equations to describe what happens at each electrode. At the anode, oxygen ions are oxidized because they lose electrons. The half equation is 2O2 O2 plus 4E. At the cathode, aluminium ions are reduced because they gain electrons. The half equation is Al3 plus 3Al. So the oxygen loses electrons, that's oxidation, and the aluminium gains electrons, that's reduction. To remember which is which, just use the simple mnemonic oil rig, which stands for oxidation is loss, reduction is gain, referring to the loss or gain of electrons. If we combine both of these half equations, we can write the overall equation for the entire electrolysis process. The reaction starts with liquid aluminium oxide and produces liquid aluminium and oxygen gas as products. Once balanced, the overall reaction looks like this. 2L2O3, L. For L plus 3O2G. So overall, the process of electrolysis of aluminium oxide involves a massive input of electrical energy to separate aluminium from oxygen. It's a great example of how electricity can drive non-spontaneous chemical reactions, and it's one of the most important industrial processes for obtaining pure aluminium metal. In the next video, we'll move on to explore the electrolysis of aqueous solutions, where water participates in the reaction and the products become a little more complex.